This video is about the file encryption feature of NTFS, which is also called the Encrypting File System, or EFS in short. We will start by looking at how to encrypt a file in NTFS. Then we will quickly observe the key changes that happen internally in NTFS when you encrypt a file. After this, we will move on to a conceptual overview of EFS and see why we need to use both symmetric and asymmetric key cryptography even just to encrypt a file. Along this process, you will also become familiar with some EFS specific terminology like FEK, user certificates, DDF, DRF, and so on. Towards the end, we will also see how to add another user to an encrypted file and the purpose behind having a file recovery certificate. By the end of this video, you should have a fair overview of how EFS encryption works. I have given a layout of this video in the comment section, so if you need to go to a specific section of the video, feel free to do that. So let's begin now. To start with, I'm going to create a text file and I'll call it enc.text. I will just fill this up with data. Save the file. Now let us see how this file is represented internally in NTFS. To do that, I open up Active Disk Editor, click on Explore My Computer, navigate to the file, right click and I select Inspect File Record. A file in NTFS is a collection of attributes. So each attribute has a certain type of information about the file. Here you can see the file has 4 attributes: 10, 30, 40 and 80. So the $80 is the data attribute, meaning this attribute is going to have the contents of the file. So when I select this attribute, to my right I can see the contents of the file. Now let me encrypt this file. So I will go to the file properties, click on Advanced, and then select Encrypt Contents to secure data. Once you do this, you will see a lock symbol appearing in the file's icon. I'm going to launch Active Disk Editor again and navigate to the file. Now if you see, after encryption, there are 2 noticeable changes to the file. So earlier we were able to see the contents inside the data attribute. Now the contents are encrypted. Another change in the file is there is a new attribute which has been added to the file, which is the $100 or the logged utility stream attribute. This attribute actually stores the details of the encryption. There is a command line tool called Cipher which can read this attribute and provide us details about how the file is encrypted. So I'm going to run the Cipher command on this file. To get the encryption details, you need to use the /c switch followed by the name of the file. So looking at the output of the Cipher command, you can see that there is asymmetric or certificate based encryption as well as symmetric key encryption which is being used here. Let us look at the details of how this is implemented. Now we will take a conceptual overview of how EFS encrypts the file. We will start at a high level and then progressively get into the details. So all the functionality behind NTFS file encryption and decryption is performed by a Windows service called the EFS service. We will look at how the EFS service actually encrypts the file. We have the file which is enc.text that we just created. This file has 4 different attributes. It has the data attribute which holds the contents of the file. When EFS encrypts the file, it will encrypt only the data attribute. All the other attributes of the file will still be in clear text. What this means is when somebody gets unauthorized access to the file, they will not be able to view the file's contents, but they can definitely view the identifying data, like the name of the file, the timestamps associated with it, and so on. Now let us look at how the data attribute gets encrypted. An efficient way to encrypt the contents of a file is to use something called as symmetric key encryption. What the EFS service does is it calls the crypto API and it generates a symmetric key. This symmetric key is also called the FEK or the file encryption key. EFS supports 2 symmetric key algorithms. Those are AES-256 and triple DES. Both these are what you would call as block cipher algorithms. So once the file encryption key is generated, the EFS service uses that FEK to encrypt the data attribute. The default algorithm in Windows 10 is AES-256 and the FEK will be unique for every file that gets encrypted. So if you have 100 files in your directory, each of those files will have its own unique FEK using which the data attribute is encrypted. All this is good, but there is only one problem here. So once you encrypt the data with the FEK, you need a location to store it securely. This is so because anyone with access to the FEK will be able to successfully decrypt the file. Since the FEK is unique to each file, you might want to store the FEK as part of the file itself. But the problem is, if you do that, you will end up doing something like this. So this is a secure lock where the code is pasted on top of the lock. So essentially, if you store the FEK along with the file, you will defeat the purpose of encrypting the file in the first place. EFS solves this problem by bringing in asymmetric key encryption. Now let us see how that works. To begin talking about asymmetric encryption, we need two keys, the private key and public key. So let us have them ready now. These keys are generated the first time a file is encrypted by that user. So this is the first step that happens. And the asymmetric algorithms supported by EFS are RSA and ECC. So this is step 1. Once the private and public keys are generated, the second step is actually to generate the FEK. So we have already covered this. The FEK is generated and the data is encrypted with the FEK. What happens subsequently is the FEK gets encrypted with the public key. So this encrypted version of the FEK is called EFEK or encrypted FEK. Now this EFEK can be stored in the file itself, because even if somebody reads the encrypted FEK, they will not be able to decrypt the data. To decrypt the data, you first need to decrypt the EFEK, and to decrypt the EFEK, you need the private key. The private key is protected by a mechanism called DP-API. So DP-API ensures that only the user test will be able to access the private key, and the public key is not protected. The public key is stored as a self-signed certificate under the user's personal certificate store. I will show you where the private and public keys are actually stored in the example that we have taken. But in terms of encryption, this is what happens. And for storing the EFEK inside the file, the EFS service actually creates a new attribute at the end of the file. It is called the $100 or the logged utility stream attribute. So the EFEK is copied on to the logged utility stream attribute along with some identifying information. And the identifying information would be the thumbprint of the certificate containing the public key and the name of the user that actually encrypted the file. This set of information is called a decryption field, because this information helps you to decrypt the contents of the file. So if the user test decides to add another user, say U2, what the EFS service will do is it will check whether U2 has a private public key pair. If the user has a private public key pair that can be used by EFS, then the EFS service actually takes the public key of U2, then encrypts the FEK with that public key. So now you get the encrypted FEK just like you got for the test user. So let us call this EFEK2. Now EFS will add details about user 2 to the logged utility stream. So it will add EFEK2, which is the FEK encrypted with the public key of U2, the certificate thumbprint of U2's public key certificate, and it will have the name of user 2. So there can be multiple decryption fields inside the logged utility stream, depending on how many users have access to the encrypted file. An organization might also want to set up a centralized recovery based on Active Directory certificates. It works exactly similar to adding a new user. But fields related to users are called data decryption fields, and fields related to recovery are called data recovery fields. So both the DDF and DRF have identical fields, just that their purpose is different. Now let us quickly take a second look at the output of the cipher command. The bottom of the output contains the information about the file encryption key or the FEK. Here it says that the data attribute of the file has been encrypted with the AES 256-bit key. And this key itself has been encrypted with the public key corresponding to this certificate. That sounds like a mouthful. I'll just show you the certificate, it'll be easy to understand. Since this is a user level certificate belonging to the test user, and I'm also logged in as test, I can go to cert manager, is certmgr.msc, and I can navigate to personal certificates, and here I can see the certificate. Within the certificate's details, you can see its public key. This is the public key that has been used to encrypt the FEK or the file encryption key. And this encrypted FEK is stored in the file's logged utility stream attribute. And when you go to the general tab of the certificate, you can see the message, you have a private key that corresponds to this certificate. It is using this private key that you can decrypt the FEK and subsequently use the FEK to decrypt the file's data. The last thing I wanted to cover was how to provide access to another user to an encrypted file. To do that, you right click on the file and select properties. So normally when you want to give another user access to the file, you go to the security tab and modify the settings. But EFS does not store its settings as part of the security descriptor, but it stores it as part of the logged utility stream. So you will have to set up permissions in a different way. So you go to general, click on advanced, and here you click on details. Here you will be able to add users who can access this file. And when I click on add, I can see the user U2 certificate because the user already has an EFS certificate. If the user does not have an EFS certificate, you will not have the option of adding that user. So I just need to click on OK here, and you can see the user U2 has been added. If you look below the users, you can see an option for adding a recovery certificate. Let us see why we need a recovery certificate. You have two options to store the public key certificate and the private key for a user. You can either store it in the local system or you can store it in a smart card. If your system crashes or you lose your smart card, that means you have lost your private key. And if you lost your private key, you also lose the ability to decrypt any of the EFS encrypted files. That is why we need recovery certificates. Recovery certificates are typically created under a recovery user. Somebody like tech support will create the recovery certificate. Let us look at the process quickly. So I have a user on this host which is called tech support. So I'm going to stop it at this and I'm going to log in as tech support user. So once I log in as tech support, I open up my command prompt. I use the cipher command to generate the recovery keys. The option to do that is /r followed by the name I want to give for the recovery files. So it asks for the password in order to protect your private key. You can see that in your desktop there are two files which are created. So the file which has the key in it, this is your private recovery key, and this is the public key certificate corresponding to the private key. Now to install a recovery agent for EFS, you need to go to the group policy settings. So I go to gpedit.msc, then under computer configuration, I go to Windows settings, security settings, public key policies, and at last I see the encrypting file system. So it says there are no encrypting file system policies defined. I go to the left pane and right click on that. There is an option to add a data recovery agent. Click on next, then I add the certificate. So it is in my desktop. There's a warning message, you can just say yes. Then you click on finish. Now under the public key policies, you have created a recovery key corresponding to the tech support user. Now the assumption behind the recovery is this private key must be stored separately from the machine on which the files are existing. Even if all the users that have access to the file have lost their private keys, you can use this tech support private key and decrypt the files. Now I'm going to switch back to the test user. And if I right click on the properties, you can see that the recovery certificate has been added. You can verify this again by running the cipher command. You can see three entries, one corresponding to the user test, one for the user U2 that we added, and the third is for the recovery certificate that tech support has created. Basically, there are three versions of the encrypted FEK in the file enc.txt. In EFS terms, you would say that this file enc.txt has two DDFs and one DRF. That means it has two data decryption fields and one data recovery field. With all that, we come to the end of this video. In this video, we have taken an overview of EFS encryption. So as a forensic analyst, you might be interested to understand two things. One is, where are the artifacts? And second is, what is the structure of the artifacts, right? We have three different artifacts here. So the first one is the encrypted file. The second one is the public key or the certificate. The third one is the private key. In the next video, we will see where the private and public keys are stored, and we will also examine the structure of the log utility stream, the certificate blob, and the private key DP API blob. See you in the next video, and thanks for watching.